Hi, thank you for the invitation to give a talk in this session. I'm learning a lot because even though some terms like Maxwell point seems to be common, I've never really worked on glasses till now. So if this all seems a bit removed, please feel free to ask questions and or give me comments and suggestions. So yeah, with that in mind, this is kind of a talk that I'm going to talk about two different topics and how they can be linked in the context of what I call spatially localized states. This is joint work that I've done with Andy Archer at Loughborough, Edgar Knobloch at Berkeley, and Alistair Routledge at Leeds. And to the first approximation, a localized state is like one of these four examples that you see on this page. And we always can identify the common features to be that there is some exponential tail and there is a distinct region of this domain which is patterned, and there is a distinct background that is different from this pattern. And in all these cases, the pattern in the middle is a dodecagonal quasicrystal. It is interesting. We'll talk a bit about it in a few slides, but it could be, for all intents and purposes, something that is just hexagons or something like this. So with that, we kind of go to why we are interested in quasicrystals. It's because soft matter experiments with tri-block copolymers, which were done by Hayashida, kind of showed that if you were to crystallize them in the third domain, in the third direction, they would just uniform, they were columnar, but in the two-dimensional plane on the surface, this is the top view of that experiment, and overlaid with scanning electron microscope image in grayscale, you have this decoration marked out in red lines. And you can see that this decoration is really rectangles and equilateral triangles. Now, this is an indication that its Fourier spectrum, which is what we see in the fourth panel here, I might minimize this to kind of, yep. The fourth panel here shows us that it has two distinct length scales indicated by the two circles. And at each length scale, we have 12 peaks. So this looks a bit like a clock face at every length scale. And this is not one of the allowed crystallographic symmetries for two-dimensional space. And that is kind of counterintuitive because there's no reason why a space-filling structure like the one we see in this image should have a Fourier symmetry that is not allowed as one of the crystallographic symmetries. And this is not just observed in a soft matter system as shown here, but earlier on in the 1980s, it was also observed that in 3 dimensions and at atomic scales now, not at nanometers, you could find metallic alloys that were coalescing into icosahedra. And this icosahedra was somehow space filling in 3 dimensions. So it was counterintuitive again to see why you would have 2-dimensional and 3-dimensional quasicrystals, which were somehow physically completely different systems, length scales being different, and so on. And further on, there were also structures like this were also observed in 2-dimensional experiments of fluids. So now you can see them with eyes, and this were happening in Faraday wave experiments at millimeter scale. So there is a requirement to ask, what's a minimal recipe to generate this kind of patterns in a model soft matter system, and that's what we're trying to do. Okay. Okay, got it. So before we go to that, I just wanted to give a small kind of sidetrack or detour about how we can, what are the levels at which we can model soft matter systems, and I want to say at what level we are going to talk about in the rest of the talk today. Of course, we can start with individual particles and apply Newton's equations or Langevins equations to understand how these individual particles interact among themselves and what structures they form when the temperature is decreased. But of course, we can approximate for the functional and stop being in a stochastic framework and talk now instead about a one particle scalar density field, which then gives us the probability of finding a particle at a location at a time and entering density functional theory. We can still approximate this by expanding this free energy, the excess free energy or the Helmholtz energy in a local gradient expansion and assuming that our mobility is proportional linearly to density. And that gives us to this mesoscopic phase field crystal model. And that is a nice level of mesoscale approximation, because in the next slide, we'll talk about how much does it cost computationally to really explore what happens in a phase field crystal system, as opposed to, let's say, individual particles, molecular dynamic simulations, right? But when we're talking about self-assembly of such soft matter, I'm really interested in kind of the two parts that are I consider to be like distinguishably different. And the first one is the first stable patch of a crystal that's formed, and that would be a nucleation event, and to understand what shapes and what patterns can nucleate and so on. Of course, we can also talk about what would be the pattern that's selected, given that at a given parameter, you might have multiple patterns that are possible, but I'm not going to talk about that today. And the second part is, once you form this patch that is stable, then this front of crystal can grow, and in the wake of that front moving, you could have defects that are left behind. And so it's about these defects and nucleation that we want to talk about in the rest of this talk. Okay, I think it's just taking a bit of a time. Hello.
Doesn't seem to appear for me yet.
Oh, okay, it's not appearing for me. So, okay, great. It's just taking some time. So, this is just a comparison of computational effort between this MD and a phase field crystal model. And what we're trying to achieve is to get an asymptotic state, a converged state of icosahedral quasicrystal. And on the left, we have a result which has 50,000 particles in a box, and with highly parallelized code. To still run it for this 120 million MD steps, it takes a few weeks to get this result. And this is a very intensive approach, because you've already just invested all that time in checking one parameter value. As opposed to that, the phase field crystal model result of a similar box size, so it's now 192 cubed points in this cube, and I've sliced an angle to show you this fivefold, the icosahedral symmetry's fivefold rotational axis. And this takes about 2 to 3 minutes on a desktop to simulate from random initial conditions. So it really allows us, mesoscale models allow us to kind of explore the parameter space and to identify interesting parameters where we might want to do more intensive calculations or computations. But of course, it being a mesoscale model, we have lost a lot of information that would be there in the microscale. So size-dependent free energy is not there at this model at this point, but it's something to think about how to add that, or coupling to a large-scale mode that is not there now. And so there is lots of work to be done at the mesoscale, but still, if you would say right now at the mesoscale is what we can easily explore. So the rest of the talk, we're going to stick at this phase field crystal level, and we want to analyze nucleation and growth of soft matter self-assembly. Okay, every slight change, it's going to be you see it before me, but that's fine. So what we have here is a scalar density field, capital U. And this capital U is now a variable in space and time. Space could be 2 or 3 dimensions. I'll show you examples of both. But in both cases, there is a Helmholtz free energy, capital F, and this dynamics is variation. So you can write the rate of change of this free energy is related to the evolution of this density. And in kind of a more detailed approach, we can split it into a linear operator and some nominal polynomial nonlinearity. So this is the simplest we can think of. So that is why it's a minimal model in some sense. And now we still have to talk about how we're going to write an expression for this linear operator. And for that, we turn to the idea of the interaction potential between two soft micelles. And if we were to think about two micelles that are far enough away, they don't see each other, and therefore the interaction potential between them is nil. And as they approach each other, they would have a first shoulder when the coronas intersect, and a second shoulder again when the cores also partly overlap. So with this kind of a 2-length scale or 2-shoulder potential, we can take its Fourier transform. So this v hat of k would be can be then related to a dispersion relation sigma in soft matter, at least with this relationship, where rho naught is the uniform is the mean density, beta is the inverse temperature, d is the diffusive coefficient, and K is just a wave number. And so what we're saying here is that this dispersion relation is having a zero, is neutrally stable at K equals 0 at wave number bulk modes. And it really selects two other length scales. And this length scale selection, so if the ratio of these length scales is irrational, then we would be predisposed to forming quasicrystals. If they were periodic, you could form periodic crystals and so on. So, and this is a tunable parameter. So with this same model, we can explore potentially in 2 and 3 dimensions, all of this pattern forming crystal and quasicrystal structures. I don't know if it's moved. I'm gonna wait. There we go. So in 2D, we choose a nominal nonlinear coefficient ratio of capital Q equals 2, and we imprint that we want to form dodecagonal quasicrystals. And the way we can imprint that is if we go back to the experiment that I really feel. One second, let me just escape full screen to go to the slide that I want to show you. Okay, maybe it's hard, but basically we can imprint this dodecagonal quasicrystal by asking what the angle between two adjacent wave vectors should be in my reciprocal space. And if that has a 12-fold rotation symmetry, then I'm effectively imprinting the possibility for this length scale ratios to be in the correct value for a dodecagonal quasicrystal to form. And we find that we also get all the crystals like hexagons and lamellae in 2D. And the interesting bit is that this quasicrystal is globally stable at a parameter where both the linear growth rates of these two length scales is negative, which means that this extended quasicrystal is somehow more efficient than even remaining a uniform liquid. It's less free energy to crystallize into this complex shape than it is to remain a uniform liquid. I'm trying to see if it, yeah. And in 3D as well, we can imprint an icosahedral quasicrystal. And for that, we have to input this irrational number of the golden ratio into our model, and we can recover columnar crystals, two-dimensional crystals, which are, you know, uniform in the third direction. And that's what you see in the first cube here. Here, the columns are not aligned with the box, but that's the reason why it looks diagonally. And in the center cube, you see body-centered cubic configuration. And we also have this kind of icosahedral quasicrystal. Again, this being the center, there is the 5-fold symmetry axis that you are viewing. And again, it seems to be that this icosahedral quasicrystal is the global minima when both the growth rates are negative. So again, this coexists with a uniform state. And this reason for me to kind of emphasize coexistence will become clear in the next slide, because that kind of brings us back to the idea of spatial localization. Hopefully. Hello. Yeah. So that's where we come back to localization, because from early 2000s, there's been lots of interest in the pattern formation community to understand what is known as homoclinic connections between two coexisting patterns. For example, in a one-dimensional simple pattern forming model, we would have the flat state being stable at the same parameters. We'd have an extended periodic state being stable. And if you can calculate the free energy cost to make each of these patterns, we can identify a Maxwell point at which it costs the same energy to remain flat or to be in a fully periodic state. And around this Maxwell point, that you can find a region where you could find a bit of the periodic state in the background of the flat uniform state. So that was in one dimension from early 2000s. And in 2 dimensions, you could also talk about how hexagons would form patches of hexagons or targets, shapes, and so on. And the question is to say, you know, yes, we know that crystals along this branch. So what we're seeing here, I might show you just a movie. Yeah, so in this movie, what we're seeing is the growth of a hexagon, and as the red dot moves along this blue branch, we see that more and more of these peaks are being added to the structure. And because we're following, in this case, a branch of full symmetry, hexagonal symmetry, we always add peaks at the middle of each face, for example, and then on either side of that peak, and then we finish out the face and so on. So it's very, structure addition is somehow symmetric. It could be asymmetric as well, but at least the simplest case, it's symmetric. And this symmetry is then decided by the symmetry of the extended state that we're connecting to. If we are growing towards a hexagonal state. By the way, this kind of movie is solution branches and not time. So this is not an evolution in time. I mean, none of the movies that okay, this movie is definitely not an evolution in time. The next two movies I'll show you would be evolutions in time. And so if we go back to this, we can look at what is the kind of nonlinear phase portrait, that a phase plot that I would get for this kind of two length scale system. Of course, we get hexagons of both length scales when one of the linear growth rates is positive and the other is negative. And we also get lamellar structures of one length scale and the other is further out. But we also have, in coexistence with the liquid state or the uniform state, which is stable in the third quadrant, a patch where quasicrystals are the globally minimal energy structures. And that means that in this area, we could look for kind of coexistence states or spatially localized states. And in fact, the black lines that you see here as domain boundaries are the Maxwell lines, are the loci of the Maxwell lines themselves. So when we try to understand what happens, now we're looking at it in terms of the grand potential omega per unit area. And what we see in green is one of the hexagons, blue is Q hexagons, and the red line is that for extended quasicrystals. And we see that breaking off in a symmetry bifurcation from this extended quasicrystals is a pink branch or a magenta branch of localized quasicrystals. And at the first point, at this point at E, it looks very small, and there is just one peak with a small motif of the quasicrystal that's visible. And as we move along, we find these kind of swallowtails. And at every swallowtail, we have a portion of that branch that is now that is dynamically stable, which means that the patterns that you see in D, C, and B are all dynamically stable locally. And this same kind of effect happens in 3D. If this is the icosahedral quasicrystal in 3D, there is an associated dynamically stable, or in other soft matter terminology, metastable states that we can find that have the same symmetry or not. But there are multiple such localized invariance shapes. So with that, I just want to go again and show, sorry. If we were to take one of these states and add noise to it, what happens to this evolution? Because, okay, I'll start the movie and talk about it. So here what we're seeing is that the noise has an evolution at a length scale and a time scale that's much slower than the evolution of my density field. And here we're having kind of starts of different hexagon patterns at different locations, and they are starting with different orientations. And that means towards the end, when everything is covered with hexagons, we're going to have grain boundaries separating regimes. We'll talk about that in the second half of the talk. And in the other, it's the same parameters again, it's just the noise is slightly different. And I've been trying to get a case where just a quasicrystal grows. So this is the best case I could show you so far. So it seems to be that one peak needs to be persistently kind of probed in the right way for it to start to become a quasicrystal, and then it just grows once the front is formed. Now, the question I was going to ask at this point, or that I was trying to answer in doing these simulations, is do we see these localized states when we start to grow? And the answer is that it's not very clear how to isolate them when they are growing, because it might be that the evolution's not, it's not going to hang around this small location because my noise is ever present in the background. And of course, the other question to ask when I'm doing this kind of noisy evolutions is, how do I actually add the noise back in? When we talked about this modeling kind of levels, we saw that in converting to an ensemble average at the density functional level, we've already integrated out or averaged out the noise. So if I'm going to add noise into this mesoscale model, what noise am I actually adding? So it looks like I should go back to looking at most likely paths instead of a nucleation and a growth event. But nevertheless, sorry,
Can
yes.
I quickly interrupt?
Yeah.
You had a little bit of a delay in starting because of some technical difficulties beforehand, but maybe, I don't know how big the second part is, but maybe we can skip to the conclusions after.
Sure. This is, the second part is about defects in patterns. So if instead of just having a uniform background, we have a pattern inside a pattern. And if you can spectrally filter it, you can look at it in a different way. And even this kind of dodecagonal quasicrystal suddenly starts to have patches of hexagon in it. And if I were to subtract this field from a reference field, we can identify where the regions of maximum change are. And there's a reason why it's hard to do that for quasicrystals, but this is the summary slide. In summary, spatially localized states can be a useful idea to investigate nucleation and defects in soft matter. Of course, about nucleation, there's problems about how to add noise back into the model. And the role of metastable localized states point to nucleation being a multi-step nucleation mostly in soft matter. And we can think of equilibria with defects or grain boundaries as localization of pattern A in pattern B. And that way we can actually account for the pinning of defects, the fact that some defects might not move after they've been formed. Thank you.
Thank you very much. A very interesting talk. There was already a question by Thomas.
Yep.
Yeah, hi. Yeah, really cool work. You might have answered it, but I'm not quite sure. When we talk, my question was about reintroducing thermal fluctuations, and I'm not sure if that's what you mean by noise or if you mean disorder.
Yes, I do. Yes.
Okay, right. Because I guess when we're talking about free energies and what phase is stable, that vibrational entropy seems to be something that could start to play an important role.
Mm-hmm.
And so I was just curious, so you have a dynamic phase field model with thermal fluctuations. Does it have hydrodynamics?
No, it is just a Ornstein-Uhlenbeck process at this point that I've coupled to the dynamics of my scalar variable. And I'm convinced that's not the way to go, but that was just me to do some, to see what happens when I do that. And I've been, is there anybody's work that you might suggest that I look up?
For coupling hydrodynamics?
For coupling hydrodynamics or noise back into a mesoscale model. That is definitely.
Yeah, well, I mean, if you look at this is in the context of lattice-Boltzmann models. Colin Denniston has done some good work on thermally fluctuating lattice-Boltzmann models. And there are some relatively straightforward paths to modeling phase field equations of motion in lattice-Boltzmann. You could probably use the same route to add thermal fluctuations there.
Okay, thank you. I will.
Yeah. For sure.
I don't see any other questions presently.
I might ask another if I can.
A short one then, and we can try to get a little bit back on schedule, but that's fine. Go ahead, Thomas.
Oh yeah, it's just you have all these quasicrystals in periodic boxes, and I'm trying to wrap my head around. That has to be something you have to think about or account for when you are identifying phase diagrams.
Yep. As in about these are all periodic approximants for quasicrystals in the infinite plane.
I see. So you're modeling
These are all periodic approximants. We can do it in bigger and bigger boxes, and they'll better and better approximate the infinite one. But yes, we are only studying periodic approximants.
Oh, okay. I missed that. I thought you had frustrated quasicrystals in periodic boxes.
No. These are perfect periodic approximants for that box, and the box size is kind of special to the irrational number at the hard fit. Yeah.
Gotcha. Okay. Yeah. Thank you.